Hello and welcome to this video where I'll share with you the sum of squares of reciprocals of odd integers, which is essentially what this thing evaluates to. And if you're not familiar with notation, is essentially this infinite series. And let's define a function phi of 2, and let's generalize it for any power and not just 2. This will be helpful in the end. So what we do with this to prove this is essentially have two approximations for the cosine function, one as the Maclaurin series and one as an infinite product, and then equate both of those and get a good result. So let's start with the Maclaurin series for the cosine function. This is very widely known and there's tons of resources available on the internet to find what it is. I'll give a short demo. So we have the cosine function, and what we do is essentially we have different polynomials that approximate the function near the y-axis or near the point x equals 0. So what I'll do is I'll increase the graph term by term so that it kind of wraps itself around the cosine function. And as you can see, this is actually pretty close to the cosine function. It is minusculely far, and at infinity the whole graph actually coincides, and this is how you would write the Maclaurin series, and it essentially expands to the same thing, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial and so on. And we'll have the infinite product for cosine. This is a bit more tricky to graph, so if you want to view it twice, I don't blame you. So we start with the same setup, the cosine function, and what we do is we know that the cosine function has an infinite number of roots. So what we do is we try to approximate the function by making different polynomials which cut the axis through these roots. And here's what I mean. This is a demonstration with the first two roots, but let's set a constant in front of the graph so that it most nearly resembles the cosine function, and the equation on the top right corner is what the graph is. And now let's repeat the process with the next two roots, and so as you see in near 0, this one is also kind of coinciding, and I'll just do a few more examples for you to see, and you'll see how this is different from the Maclaurin series. This is where we were when we had the smaller grid. So we have the first two roots, 4, 6 and then 8. But one thing to note over here is that this one expands way faster horizontally than it actually wraps itself around the graph, which means it is not as efficient as the Maclaurin series, but it still works, and at infinity it's still cosine. So this is what the function is actually, and there's a very general pattern here which allows us to write it in a form called an infinite product, and this is essentially the thing in the previous scene. So now here is how we produce the result. With both of these two approximations, which are essentially the same, the cosine function, what we do is we equate one to the other. So we have the sum equal to the product, and I'll do a little bit of algebraic manipulation here. So we have the product. This is just the first three terms, guys. So I'll spare the labor work. I'll expand the first two brackets, and I'll just multiply the third one into it as well. And expand the left side with it. So what we see here is that there's different order terms on both sides. So we do what's called comparing coefficients, which is essentially having the x squared terms equal to each other, because, well, both of these are the cosine function. And let's just look at those terms individually, and if you actually manually multiply the terms, you'll see that there is a minus 49 pi squared and so on term. And so we factor 4x squared over pi squared from the thing, and as you can see, we already have an infinite series that we want to derive rather, and then we move the factor term to the left side to produce this beautiful result. It is super surprising how pi squared over 8 is the answer of our original function, the phi of 2, which, if to remind you, was actually defined like this. Now, in the beginning, I told you about phi of s, which is for any real number. And so, let this be a challenge to all the viewers out there. How would you define phi of s? I'll give you a hint. It is by comparing coefficients, comparing the different coefficients rather of the infinite product to the Maclaurin series. This video was made with Manim, a mathematical tool to animate your proofs.